Hello, everybody. How we doing today? I hope everybody's having a good day. Okay, we are working on exponents here. So let's see. Now remember, if you're stuck on something, if something's bothering you, if something you don't get, first of all, the best thing to do is just get here at this time. If you get here at this time, I'm just trying to put it up the display here. If you get here at this time, we could talk about it. We could see. You could be like, this is what I'm stuck on," and then you just post say something in the comments, say something, put it in chat. Okay, let me just make sure we see myself there. There we go. Yeah, just post it in the chat. Say we're watching here. So far we got 2 people watching, so hopefully. So what we're working on this week, we're working on exponentials, remember. Okay, and now remember how that works, though. Let's go to the document camera here. Okay, let's just do a little review because it's been a long weekend. Okay, so remember, for exponential functions, exponential. Okay, now remember where the variable is. Okay, the variable is in the exponent. Remember that. So it's like y equals 2 times 4 to the x. You see how the variable up here is right there in the exponent. That's the thing you got to pay attention to. Where's the variable? So I saw people turning stuff in, and they're writing it like this. Now, it's not down there. You got to put it up there. The exponent is up there. And we got 2 different types of exponents. Here's the formula. Y equals a times b to the x. And remember, the b can't be negative. So it's bigger than 0, but less than 1. The word we use is we call that decay. Like decreasing for slope. This is decay for exponents. And it looks like this. It starts up top and goes down low. And things that happen like that is, you're losing something. Okay? It slowly decays. Half-life, for example. They could date the dinosaurs lived 4 billion years ago because carbon decays like that. Now, if b is greater than 1, we call that growth. And it looks like this. And money, finance, grows exponentially. We'll talk more about that today. You see that? And so the b is what we look for, just like slope. B is the deciding factor. Now, right here, the most important point right there, that's the y-intercept. And the y-intercept is a. So this point is, for example, 0, a. 0, a. That point is a. Okay, so the b is the rate of growth, and a is the y-intercept. Remember that we were talking about that last week. Okay, now remember, if you're stuck on something, if something's bothering you, all you got to do is just, send a message, ask Mr. Byrne, ask myself, send an email, post something on Schoology, ask a question, because the assignments are, one a day. We're having one assignment a day, and a lot of people are turning those in, and a couple people are not, so make sure you turn those in. Let's go through the last 2 together right now. Okay, here's what we're working on. Okay, this was Mondays and data modeling, and now we're going to undo stuff, so get ready. Okay, you bought a car, $16,000. The car is expected to lose value, depreciate, we say. Okay, and that's decay. Depreciate, decay, that's what we're talking about here. The car decreases $80 to $800 per year, that's linear. The car decreases 1% each year, that's exponential. Remember, decreases minus 800 per year, minus 800 per year, every year, minus 800. Whereas a percentage is times. Okay, you have times. Now remember, if it decreases 4%, you only have 96% left. Like you lost 4%, so you only have 96% of the original problem. That's be tricky there. Be careful right there. Because this is just exactly what it says in the problem. Okay, but if it decreases by 4%, you only have 96%. You see, because 100% is everything. If you lose 4%, you only have 96% yet. So the equation for linear was going to be y equals, you start with 16,000, but then you go minus 800 every year. And they're using x right there. Whereas if it more and more accurate, it decays like this, then your equation is y equals 16,000 times. Now remember, we can't say percent, so 0.96 to the x. You see, now that's very important. That's the thing to pay attention to. Make sure you're putting 0.96 right there. Okay? And there's other ways to do it, but there is the value of the car. If y represents, the value of the car is, if it lost 4%, it's only 96% of what it started with. Everybody see that? So a couple people were asking about that one. Okay, use the constant percentage rate to find exponential model. Basically what they're saying is, like we've always been saying, this is all it's saying here. If r, the rate, you see how they're saying if the rate is greater than 0, that's growth. So if it's increasing, if r is less than 0, that's decay. So what they're doing is they're doing that exact example that we're saying up here. This number, you have to go 1 minus 0.04. You see that? That's where I got that from. Because if it's decaying, you're losing 0.04. So remember the formula we had last week, 1 minus. That's what we did right there. Let's do another example. In a particular area, homes have depreciated 3%. The home was purchased at $100,000. How can you tell by the words that you can use an exponential, to describe the relationship? Well, there's the word decay or depreciate. This is just like decay. When it's depreciating, and also a percentage. When it's a percentage, we're not adding or subtracting. Remember, when you buy something at the store and it's 20% off, they take the price and they multiply it by 0.2. If it's 25% off, they take the price and multiply it by 0.25. Remember, percentages are always multiplied. So there's another hint that we're dealing with exponentials right there. So let's see what we got. Let's take each step. So we start with the y-intercept. That's how much the home is. That's what we're starting off. And now remember, you could go 1 minus 0.03 because it's depreciating. And then whatever years the home value after, remember t is after 2013 because the y-intercept is 2013. So that's where we get and people hopefully are understanding that, 0.97 to the t. You see? Because if it's depreciating, if you're losing 3%, you only have 97%. So predict the value of the home after 10 years. Y equals, if every year you lose 3%, let's do we can make a chart, put a little 10 in there. Let's do it the long way and then the short way. The long way is each year we lose 3%. So each year we only have 0.97. So after 1 year, the house is only worth $97,000. And then after 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years, $73,742. Now, of course, we could do the fast way. Use the formula. Use our formula here. Plug in the 10. Watch how I type it. 100,000 times 0.97 to the, now remember where your to the button is. Your to the button is right there under exponents. To the 10. And look at how I get the same answer. $73,742. You see that? That's called depreciation. That's decay. Here's another depreciation. Half-life. Half-life is when you have half of what you started with. If something decays exponentially, look at the words there. If a quantity decays exponentially, the half-life is the amount of time it takes for the quantity to reduce by half. So for example, we would like to find the half-life. It says use the information in example 6. And figure out when the half-life is. Let's take a look. Round your answer. Now we could use the table or we could keep going on our calculator. Let's try it out. How many years would it take for us to have half? Now remember, that's 10 years. And we'll do the table also, but then you times it by 0.97 again. That's 11 years, 12 years. Remember, we're looking for 50,000. 13 years, 14 years, 15 years, 16 years, 17 years, 18 years. We're getting close. 19, 20, 21, 22. There we go. Somewhere between 22 and 23 years, and we got half of what we started with. Let's show that on the table. Now, remember to do the table, you got to put the equation in. Let's clear off the old equations. You got to put your equation in. Our equation was 100,000 times 0.97 to the x. Okay? And then we go to our table. Well, let's go to our table right there. And if it's not 1, it doesn't start at 0. Okay? If your table doesn't start here, go to table set right here above window. Second table set, and just go to 0 and your steps by 1. Change that to 0 and 1, and then when you go to your table, it'll start there. And now we're looking at our table. Remember, you could pause the video when you're watching it if you're confused by that. Okay, pause the video and try it on your own first, but take a look. We reach 50,000 somewhere between 22 and 23. Everybody see that? That's how we get the half-life. Round your answer to the nearest whole number. Okay, so somewhere between 22. So let's go. Which one's closer? It looks like 23 is closer. So we'll say about 23 years. Now there's a way to calculate that exactly. We're going to show that in a little bit. Okay. Now, let's take a look at using our calculator. Use the regression equation. Remember how we did the linear equation and the quadratic equation? We're going to do the same thing with the regression equation. Okay, watch what you do. Okay, so back to our stat and edit our list. Now, you might have lists from there before. Okay, clear those lists out. Remember, all you have to do is go above list 1 and hit clear and enter. It'll clear those lists out. And then the first one, let's enter it here, 0, 1, 2, 3, 4, 5, 6. And then list 2, let's see what we got. It's 80, 72.3, 63.2, 55.7, 51.8. Just entering the information in the calculator. 40.9. There's our information entered. Okay, now back to stats. And now remember, when we were doing linear regression, that was number 4. When we were doing quadratic equation, that was number 5. Well, if you keep going, you have exponential regression. You see that? That's number 0. Okay? And just like before, just like we did, you enter, select that, list 1, list 2, and go down to calculate. And there's our A and there's our B. Okay, now remember, refresh your memory. Remember A, so let's write the answer down. A was 800, or 80. A was 80.22. B was 0.889. So right away I know it's decaying, which makes sense. These are going down. That's decay because that's between 0 and 1. Remember, decay is between 0 and 1. Rewrite the equation in this form. So A of t is equal to A is 800, or A, I'm sorry, I keep saying 80, P minus 1 plus. All right, take a look at this situation here. This number in the middle here, I shouldn't write 1 plus. I should just, the number in the middle is 1 minus, would be better to say, what this is write it at, is 0.889 to the t. That's the number in the middle. It's less than 1, so it should be minus right there. Okay? So what's the percentage change? Well, if this is how much you have every time, it looks like we're losing about, now remember the number, if that's 1 minus the change is 0.889, R looks like 11%. Where it looks like we're losing 11% every time. Now watch what I did there. That could be a little confusing. So we have this number here. This is the decay. The decay number is 0.889. Okay. Now remember, 1 is the border. So how far away from 1 is 0.889? You just get your calculator out and you go 1 minus 0.889, and we get 11.1, 11%, or 0.111, 11%. Okay, so it says approximately what percentage change it decays 11% is about what percentage change we got. And what does the answer to E, mean and content of the problem? Just like we said, it's decaying about 11%. Okay, so what would you think you'd have after 14? We plug it into our equation. 80.22 times 0.889 to the 14. And let's see what we got. 80.22 times 0.889 to the 14th. And it looks like we have about 15.4, let's go 5. 15.45 right there. You see how we're just using our table, trying to make an equation to predict. We would like to find the half-life. Okay, now remember what half-life is. Half-life starts at 80, so half-life would be when it hits 40. So we're looking at around 6 hours. Let's see how the calculator does it. So what I'm going to do is, we did this before, I'm going to put the equation in. 80.22 times 0.889 to the x. There's my equation. And then I'm going to put 40 in there. And don't hit graph, remember, hit window. And we're going from 0. Looks like we thought it intersected about 6, so I'm going to go from 0 to 10. And it starts at 80, so between 0 and 100 is good. I hit the graph. Here comes the decay, which looks pretty good. And then here's the horizontal line. There's your intersection right there. How do we find that again? Here's where you pause the video and say, okay, wait a minute. I can remember how to do it. I'm just waiting here. Second calc and intersect. And then you go to as close as you can. Oop, I'm going the right way. Yeah. Go as close as you can. Here it comes. And then I just hit enter, enter, enter. And there it goes. It calculates it at 2. It's 40 at 2. Wait a minute. That's not. Did I enter the equation right? 80.0 to the x. No, that looks right. 80. Hold on. Maybe I entered the equation wrong. Oh, I got 2 x's. Oh, no. Look at that. My mistake. I was like, that didn't look right. Let's delete that and try it again. There we go. To the x. Let's try our graph now. All right, looks a little different. But still, decaying. There's a horizontal line. Let's calculate it one more time. See, always check your work. Enter, enter, enter. That's better. That's better. My prediction is about 6. Okay, so my prediction is about 6 right there. That's a little better. Take a look at that. Especially if you did it correctly at home. All right, one more. Let's do this again. Let's try this again. Here we got a different situation. Okay, another model. We're going to do the exact same thing here. We'll try it again. Okay, now let's think about our situation. This is 0. So it help every decade. Okay, it's every decade. So this is 1 decade, 2 decades, 3 decades, 4, 5, 6. You get the idea. 9, 10 decades. Okay, because we're talking decades here. Let's see what we got. So we go to stats. Just do it one more time. Stats, edit, and let me clear off list 2. And list 1, well, that's nice. 0, 1, 2, 3, but I got to enter more here. So I go 6, 7, 8, 9, 10. There's for list 1. Did I do that right? 0, 1, yeah. And now for 0, it's millions of people. And 1750, 1860, 2070, 2300. See, we did this before. 250, 3040. Remember, ask a question. Send Mr. Byrne if something's bothering you. You got to say, I don't get it, or I want to talk about it. That's always fun. Oh, all right. So enter the data. Okay, now we come up with our equation. Where was it again? Here's where you pause the video again and see if you remember how to get there. You pause the video. All right. Video pause over. Let's show it. We go to stat, calculate, and all the way down here, 0 is exponential regression. And enter, enter, enter. And there is our value. So we have A is 1447. It says round to 3 decimal places. 144. And B is 1.146. So what do we see about that? So now pause and analyze. Okay. A, which represents the y-intercept, the population, our approximate population in 1900, and B is the rate of, okay, here it goes. Is it growth or decay? See, dramatic pause right there. Growth or decay? Since it's above 1, it's growth. Or just look at the numbers. The numbers getting bigger or smaller? We're growing. Okay, so we got A of t is the population, is the y-intercept, I should say. B is 1.146 to the t. You see that? So what percentage are we growing? Now remember, that's where that 1 comes in. 1 is the border. So is this above 1? So how much above 1? It's either 1 plus r or 1 minus r. R is the rate. So the percentage is about 14.6% growth. What does this mean in the problem? The population is growing at about 14.6% a year. A decade. Each decade it grows about 14%. So what would the world's population be in 2050? Well, 2050 would be 15. So t is 15, because remember, we're talking decades. So I get my calculator, got to enter this in the equation. I go 144, there's that, times 1.146 to the 15. And my population looks to be about 11175. Remember, this is millions of people. So we're at 11 billion people. Millions of people. Now use the intersection on your calculator. Let's figure out the doubling time. All right, let's see what it's doubled. And we probably could see it. If we're starting at 1,650 times 2, it doubles at 3,300,000,300. That looks like right here. So it looks like our answer is going to be somewhere between 6 and 7. Let's see if we use the calculator. Let's see what the calculator says. Let me enter this correctly this time. 1447.144 times 146 to the x. Enter that correctly. Doubling, as we said, is 3300. Now I got to check my window. You see, I'm thinking it's intersecting about 6, so that's okay. But wait a minute, my numbers are huge. So I'm not going to go from 0 to 100. We're going to, I'll say 4,000, so which is 4 billion, because I know it doubles at 3. We said 33. So let's see what happens now. There's my graph. Here's the growth. Looks exponential, pretty nice. And there's the line. So second calc, how do you find it again? What number are we looking for? Intersect. And enter, enter, enter. Just get as close as you can, and let's see the calculation says. Okay. 2.4. Did I do that again? Because 2.4 shouldn't be. Oh, did I enter my equation wrong again? Did I mess it up? I thought I 1.4 to the x. I did it to the x again. How did I keep doing that? Okay, I did it again. Delete, delete. Okay, that's better. How do I keep doing that? Let's try it again. There's the exponential growth. There's the horizontal line. Yeah, I don't know why I keep doing that. And I go second calc. Enter, enter, enter. Get as close as you can. Yeah, that's better. So the end looks like about 6. So when is it double? It looks like in 1960-ish. about 1960 it's going to double. Now, we will work on how to find that exactly in a little bit. Okay, there was the 3 worksheets that we had due today and tomorrow. Now, remember, all the grades are updated. It's either you turned in the worksheets or you didn't turn in the worksheets. Make sure you do that. We're going to have a quiz on Friday on this, so make sure you're keeping up to date. Now, I think grades are updated. If you think they're not, send me a message, send me an email or something, post something saying, hey, Mr. Noah, take a look at my grade. I turned this in already. Okay? All right, I hope everybody has a good day, and we will see you. We're going to Thursday because we'll give you tomorrow to work on this, the next 2 assignments, and then Thursday we're going to get together, and Friday's a test. All right, have a good day, everybody.